Hello and welcome to our lesson today. We are looking at the topic integration and we want to understand what integration is and the specific subtopic that we'll be dealing with in this particular presentation is reverse differentiation. Now remember, in the previous topic differentiation, we learned how to determine the gradient function of a given curve or function. We were able to understand that provided a function y, which is a function of x, then one can be able to determine the gradient function by basically differentiating the function y. In this topic, we will learn the reverse process of differentiation, and that involves us understanding how do we determine the function given its gradient function. Now, consider the lines shown in the diagram below. The diagram is indicated on the other side of the screen. The lines all have a gradient of 2. Therefore, their gradient function dy dx is equals to 2. Generally, the lines whose gradient is 2 are of the form y is equals to 2x plus c, where c is the constant also known as the y-intercept. So for n given gradient, an infinite number of lines can be drawn. Their relative positions can be distinguished by the value of c. So let's take our very first activity, our activity number 1. For each of the following, give 3 possible equations of a line whose derived function dy dx is part A -2, part B a half, part C 3, part D 6. So how do we proceed to be able to determine 3 possible equations given that we have their gradient function? So for the first one, the equations will be of the general form y is equals to -2x plus c. By assigning c 3 different values, 3 equations will be y is equals to -2x plus 3, y is equals to -2x minus 4, and y is equals to -2x plus 10. So basically, given the gradient function, one can be able to determine the general form of the equation before it was differentiated to determine the given gradient function. And usually, for a straight line, that general form will be y is equals to mx plus c. You'll notice that the equations are all of the form y is equals to -2x plus c for the first one, y is equals to a half x plus c for the second one, y is equals to 3x plus c for the third one, and lastly y is equals to 6x plus c. Of course, where c is a constant in each of those particular cases. Now, by assigning particular values of c, we can be able to determine the equations, the specific equations of these particular functions. Further, we know from the topic differentiation that the gradient function is not always a constant. For example, if dy dx is equals to 2x, then this must have come from the function of the form y is equals to x squared plus c, where c is a constant. Now let's look at our very first example, our example number 1. Find y if dy dx is 3x squared, 4x cubed, a half x, x cubed. In this example, we are required to determine the respective functions whose gradient functions are provided in these 4 questions. For the first one, we were told that dy dx is equals to 3x squared. So therefore, for us to be able to determine what the function was, we integrate dy dx, which is 3x squared. And for us to be able to do that, we increase the power of x by 1 and divide by the same power. And then we add our arbitrarily constant c. So therefore, the first one, we are getting that y is equals to x cubed plus c. For the second one, in the same manner, we are provided with the gradient function, which is 4x cubed. For us to be able to determine what the initial function was, we integrate 4x cubed, and for us to do that, we increase the power of x by 1, which gives us x to power 4, and then we divide by the same power 4, which will give us y is equals to x to power 4, and then we add the constant c. The same way for c, we also integrate a half x, giving us x squared divided by 4 plus c. And then lastly, for the fourth one, we also provided the gradient function, so we integrate our gradient function, giving us y is equals to x to power 4 over 4 plus c. Notice that in each of these 4 cases, the power of x is increased by 1 and divided by the same power before adding c. For instance, if we can look at the first one, we have dy dx being equal to 3x squared. So for us to integrate that to increase the power of x by 1, so that gives us, this is going to give us 3x to power 3, and then we divide by the same resulting power, which is 3, and then we add our c. So the 3 and these 3 will cancel out, so that we are remaining with x cubed plus c, hence our function becomes y is equals to x cubed plus c. So for all the other 3 are also done the same way, and the resulting answers are indicated in each of those particular cases. So this process of finding a function from its gradient function is what we call integration. So when you're told to integrate, what that basically means is that you need to determine what the initial function was from the given gradient function. Now the table below shows some gradient functions and their respective functions. So we have on the first column, we have dy dx, which is our gradient function. And on the second column, we have the function y. Now, for the first gradient function that you've been given, it is x squared. When you integrate that, we are going to have x cubed over 3 plus c. Remember, we said for us to be able to integrate x squared, we will have, if we have x squared, and we want to integrate this with respect to x, this will be able to give us x. We raise the power of x, we increase the power of x by 1, so that's going to be 2 plus 1. And then the resulting power, we divide by x, so 2 plus 1. And then we add the arbitrarily constant c. And this will basically simplify to x to power 3 over 3 added to the arbitrarily constant c. So hence the result x cubed over 3 plus c as indicated on the second column. Similarly, for x cubed, we're going to have x to power 4 divide by 4, add our arbitrarily constant c. For x to power 4, we are going to have x to power 5 divided by the same power 5, adding our arbitrarily constant c. For 2x cubed, we are going to have 2x to power 4 over 4 plus c, of course, which this particular result can be able to simplify to these 2 and the 4 can cancel out, so that you're going to remain with x to power 4 over 2 plus arbitrarily constant c. And then lastly, I have x to power 5. You're going to have, we increase the power of x by 1, giving us x to power 6. We divide by the same power 6, and that will give us x to power 6 over 2 times 6 plus the arbitrarily constant c. Again, this can simplify to x to power 6 over 12 plus c. From the example already done, we notice that to integrate, we reverse the rule for differentiation. Remember, in differentiation, we multiply by the power of x and reduce the power by 1. Now, in integration, we increase the power of x by 1 and divide by the new power. In general, if dy dx is equals to x raised to power n, then our initial function is going to be given by increasing the power of x by 1, which you're going to have x raised into power n plus 1, divided by the new power, which is n plus 1, and then adding the arbitrarily constant c, where c is a constant and n can never be equal to -1. We note, since c can take n value, we call it an arbitrary constant. Time to test yourself on what you've learned in this lesson. Pause the video and try working out these questions. In summary, in this lesson, we've learned how to integrate. Provided the gradient function, we can determine what the initial function was by using the rule increasing the power of x by 1 and dividing x by the new power, and then adding the arbitrary constant c. Thank you for joining me. See you on the next lesson.